if you've been to these reviews before, you know I always say there's two pieces of advice. One is do problems. These are just some problems. You shouldn't be like, okay, if I can do these 14 problems, that's all I need to know. Certainly it's the case that if you can understand what we talk about today, you'll be in good shape. These problems are across a broad range of topics, but these are not going to be necessarily exactly like the problems on the exam. Some of these problems will have nothing to do with problems on the exam because there are many more topics than the questions on the exam. You can go back and look at other reviews. You can go back and look at your quiz problems. You can go look at old exams. The more that you do, then the more that you'll see different ideas, and also you'll get used to sort of pattern matching. And the better you get at pattern matching, the better off you are. And the second thing is take care of your health. And this has taken, extra importance recently. Please stop licking things. Yes, lots of things look delicious, but it doesn't mean you have to taste everything. And go outside, take a walk, relax, get enough sleep. But please, stay healthy. And this also includes mental health as well. All right, so we've got 14 problems. Let's get started. So, number 1, you are constructing a solid where for 0 less than or equal to x less than or equal to pi, you draw the curve z equals tangent of 1/4 x on the wall. So sort of here's the setup. You're going from 0 to pi, sort of where the wall meets the floor. And on the wall, here's this curve, tangent 1/4 x. Along the floor, you draw secant 1/4 x. So you have the two curves, tangent, secant. And then for each x, you construct a right triangle where on the height, you go up to the curve on the wall. On the base, you go out to the curve on the floor. And the question is, what's the volume? And everything here is measured in meters. Okay, so we know a couple of things. We should talk about things. What's the key word here? Yeah, we see it's a volume problem. So we say, all right, when we think about volumes, there's just a handful of things that we know. And they're sort of generally fall into two big categories. One is volumes of revolution, and the other category is everything else. And volumes of revolution, this is not that. Because if it's a volume of revolution, we expect things to be nice and see sort of circles everywhere in some shape or form. So this is the other category. In fact, the other category, this is the first thing we talked about. And so this falls into the situation where we say that the volume is found by adding up, which is what integrals mean, a to b, of the area of a cross-section times the little width. So that's how we start by talking about volumes, is we think about slicing things into small pieces and saying, okay, how much does each piece contribute? And by the way, you're going to see that I'm going to consistently write things in this sort of very generic format, because I find it's very convenient to write it that way, because it's easy for me to adapt to whatever situation I'm in. So when we talk about an area, we're talking about an area of a cross-section. So for example, there's this triangle, that's one of our cross-sections. So we have to start thinking, well, in our case, what do we have? We're told, from 0 to pi. So 0 over back here is pi. So 0 to pi. The area, well, I need to find the area of this triangle. Well, how do you find the area of a triangle? 1/2 base times height. So there's a 1/2. What's our base? Yeah, secant of 1/4 x. What's our height? Yeah, the tangent. That's the wall. And then, what's our width? dx. Okay, good. Now we have our integral. Of course, we have to actually figure out how to integrate this, but maybe we have a way. So it looks like we have secant tangent. Do we know how to integrate secant tangent? Yes. All right, good. I like that answer. So 1/2. What's the integral of secant times tangent? It's secant. And by the way, in case you're wondering, are we going to have to do really any crazy integrals? And the answer is no. Any integrals that you do get asked to perform are going to be integrals that are very straightforward. No techniques that we learned at the beginning of the semester. They're all going to use techniques that you should have known coming out of Calculus 1. That's a sign, by the way. If you're on an integral and you're like, I don't know how to integrate this, well, probably you're either making a very serious mistake, go back and check your work, or maybe you're in the wrong class. But I'm going to be optimistic. Go back and check your work. Okay. Do we need anything else here? Oh, we need a what? There should be a 4 because we have to compensate for that 1/4. So, times by 4. Good. And now evaluate 0 to pi. So, we'll have a 2, and we'll have a secant of pi fourths minus a secant of 0. Well, we should know these numbers. What is secant of 0? It's 1. What is secant of pi fourths? Square root of 2. Now, in case you're a little cautious here, secant of pi fourths is the same as saying, well, 1 over cosine of pi fourths. And cosine of pi fourths is a little bit more familiar. That's 1 over, and a lot of people think of it as square root of 2 over 2. If you flip it, that's 2 over root 2. And then if you rationalize it, you end up with square root of 2. Or you can just memorize it. All right, so we end up with 2 times square root of 2 minus 1. Now, it doesn't ask for it, but suppose we said, what are the units? In this case, what are the units? Yeah, meters cubed. How do we know? Because everything's measured in meters. All right. And now, that's it. We're done. Ah, good, good. That one's not so bad. And oftentimes for these problems, once you are asked for volumes and you see that the cross sections aren't looking like circles, it's just like, all right, find the area of the cross section, add them all together, and we got our volume. Life is good. Okay, number 2. Find the volume when the region 0 less than or equal to x, less than or equal to pi, and 2 root x sine of x is less than or equal to y, is less than or equal to x plus 2 sine of x, is spun around the x-axis. So in other words, it's this yellow thing here, and we're spinning it around the x-axis. Okay, well, that's interesting. So, again, keyword, what do we see here? Volume. And we see it's a volume of revolution because we're spinning here. So we know we're going to use one of our volume of revolution techniques. In fact, there's 2 of them. And so we need to know both of them. So the question is, which one do we use? So let's figure it out. So in this case, should we integrate with respect to x or with respect to y? We should integrate with respect to x because these functions are given to us as functions of x. And they're terrible to try to rewrite them as functions of y. So we're not going to do that because we like ourselves. And we don't want to be miserable. So that says that what we should be thinking of is, since we're integrating with respect to x, we're going to take just a little tiny slice and ask ourselves, what happens to that little tiny slice when we spin? And if you take that little tiny slice and spin it, what you'll see is a certain shape emerges. And that shape will tell you what technique to use. What do we see? You see a washer. Yep. So that says we're going to be using our washer method. Good. So, how does the washer method work? So, the washer method says the following. If I want to find the volume, I'm going to add up, which is what an integral is, adding stuff up, a to b, and I'm going to think of it as taking a big circle minus a little circle. That's what my area of my cross section looks like. So I think of it as pi, and then I do outer radius squared minus the inner radius squared, and then I have a little bit of thickness on the end. So that's what the volume becomes. So now let's work through our pieces. So for our case, What are a and b? 0 and pi. Because the problem told us 0 and pi. Now the pi becomes pi. The outer radius. Well, what you do is you figure out where you're spinning around. In this case, we're spinning around the x-axis. And what we do is we go up to the furthest curve out. That's the outer radius. So which curve is the one that's further out? Yeah, x plus 2 sine of x. And we're careful here because, we're going to x equals 0. So we could go around a different line, but we're going to just 0. So we can spin around any line. So x plus 2 sine of x squared minus the inner radius. Well, you go from where you spin to the inside curve. Which curve is that? 2 square root of x sine of x. Okay, squared. And our thickness? Dx. All right, good. Now at this point, we probably have maybe half our points on a problem. And you might be thinking, yeah, it didn't do very much. It doesn't take very much. A good start is worth a lot. So you got to work and get that good start going. Okay, so, well, the pi can come out. What do we do next? Yeah, I've got to square it. So we're like, x squared, great. I can integrate that, good news. What's the next term? 4x sine x. And you're probably thinking, no, that looks like integration by parts. You said there wouldn't be any. Well, hold on. Let's see what happens. What's the next term? 4 sine squared x. Now, that's the first term. Minus what? 4x sine x. What? It's almost as if they had planned, because they did, that the parts that would be the hard things to integrate would cancel out. Now, it's not trivial. There's still something left you have to think about, which is the sine squared of x. What do you do for that? Yeah, power reduction. And you need to know your basic trig identities, especially because we did a lot of stuff with polar coordinates at the end. So power reduction, you need to know that one. So what does sine squared of x become? 1 minus cosine 2x over 2. So let me write this up one more time, and then we'll do the integral. Pi integral 0 to pi. We have the x squared. Then we have the 4 times a half makes it 2. So plus 2 minus 2 cosine 2x. So that's our integral. And none of that is particularly hard, I hope. So let's integrate. Integral of x squared? Third x cubed. Integral of 2? 2x. Integral of 2 cosine 2x. Sine 2x. And the sign will not change. So minus sine 2x. Evaluate that from 0 to pi. So we plug that in. We'll get a pi, a 1/3 pi cubed, a plus 2 pi. Sine of 2 pi? 0. And if we plug in 0, we'll get 1/3 0 cubed, which is 0. 2 times 0, which is 0. Sine of 0, which is 0. Which means that's it. And there's our answer. Pi times 1/3 pi cubed plus 2 pi. All right, good. Well, on to the next one. Okay, let's do our next problem. So number 3, set up an integral to find the volume when 0 less than or equal to x less than or equal to 1 and minus 2x less than or equal to y less than or equal to 1 over 1 plus x to the fourth plus 3x to the fourth minus 2x is spun around the y-axis. So this is our shape here. It's kind of a strange shape. And we can kind of vaguely guess what it might look like when we spin it. It's kind of a strange thing. Okay. Right? We're going to spin. Now, what are we going to do? Well, first off, we should integrate with respect to x. Why? Well, look at this function. It's a function of x. And we don't want to solve x as a function of y because, good luck, not going to happen. Okay, so what does that tell us? Well, it tells us that when we do our slices, we're going to think of it as small changes in x. So our slices look like that. And so when we spin these around, what do we form? Well, we're not forming washers anymore. We're forming shells. So, shell method. Okay, so how does the shell method work? So the shell method says the volume is, you add up between your endpoints, 2 pi, and that's always 2 pi. Then there's a radius, that's how far you are from where you're spinning, your height, and of course, a thickness. Now, let's look at our case. Well, where are we adding between? 0 to 1. Okay, it's not so bad. 2 pi is 2 pi. Now what's the radius? Well, it's how far your slice is from where you're spinning. In this case, that's our distance to the y-axis. So the radius, in this case, is x. What's the height? Well, it's this measurement here. So it's not down to the axis, it's between the curves. So we take the top curve, so that's this 1 over 1 plus x to the fourth plus 3x to the fourth minus 2x, and we subtract the bottom curve, minus 2x. And our thickness, well, that's our change in x. Now, you might notice something really nice happens right away. This minus 2x cancels. In fact, we could have put any function we wanted here, something really exotic, hard to integrate, and be like, we can't do it. But they would cancel out. And we're like, mwahaha. We'd make a hard, impossible problem actually possible. Now, where do we go from here? Well, we're really left with a couple pieces. So let's see what they are. In the first piece, we have 2 pi x over 1 plus x to the fourth. And then the second piece, we have plus 6 pi x to the fifth. All right, so now we just have to think about how to do these pieces. Now, this last piece right here, this we have a term for. It's nice. So we're good to go on that piece. Now this piece, we're like, not so clear. Not so clear. So maybe we should do a little bit of work on the side to sort of figure out the details there. Well, it's not so crazy, right? I mean, we're told we can do it. So what would we do? Well, we'd have our 2 pi x over 1 plus x to the fourth, and we start thinking about what looks like this. And there's not very many things we have to think about because there's already a list of 10 integrals we need to know. And the one that seems to jump out to me is like, there's something like arctangent has something like this, right? 1 over 1 plus u squared. That's easy. Well, that's not a square, that's a fourth. But I can think of it as 1 plus x squared squared. Aha! Aha! Now, here's an idea. Let's do a substitution. So let's let u equal x squared. Then du would be 2x dx. And look, I have a 2x dx. So what would happen if we did the substitution? Well, we'd have to update our bounds. Now, the old bounds were 0 to 1. X equals 0. X equals 1. Those were our old bounds. The bounds that were our new bounds, the ones that we're going to use, are not the 0 to 1. They're now 0 to 1. Now you might say, what? Well, because 0 squared is still 0. 1 squared is still 1. So we did actually change the bounds. The 2x dx becomes du. So upstairs we have a pi du. And then downstairs it's 1 plus u squared. Now we're good to go. That's on our list. So in particular, we get what? Well, so we're going to get pi, then we're going to get arctangent of u. and evaluate from 0 to 1. Now, arctangent of 0 is 0, so that's nice. Arctangent of 1, do you remember that? Hope you do. Well, we like arctangent. So that's pi times 1/4 pi. Or if you like, 1/4 pi squared. Okay, so that's the first piece. So now we just put our pieces together. So our first piece we have, and again, remember, that's this integral. We already did that on the side. So that's 1/4 pi squared. We did a little bit of substitution, cleaned it up. Now we still have to do this other piece. But we said this was happy. Why? 6 pi is a constant. I just have to integrate x to the 5th. Well, the integral of x to the 5th is x to the 6 divided by 6. That makes the 6's cancel. So pi x to the 6, evaluate from 0 to 1. Well, that's as easy as pi. And that's our answer. Good. So it's good to be able to recognize when do you use different methods. So volumes of revolution, there's two methods. There's the washer method and the shell method. And we want to make sure we're able to do both. All right, good. Let's go to do this one. All right, for 1 less than or equal to x, less than or equal to 5, find the length of the curve y equals 1/2 times x squared of x squared minus 1 minus the natural log of x plus the square root of x squared minus 1. Okay, yeah, that one feels a lot easier. All right. So, let's suppose we have this. What can we do? Well, what's the key word here? Length. Okay, now for length, it's actually interesting. By the time we hit our exam, there's 3 variations of length, so you should know them. So what are they? Well, one variation is the y equals f of x. And if you see that, you integrate the square root of 1 plus f prime of x squared dx. So that's our first variation that we learned. The second variation is we did parametric curves, x of t, y of t. And if you see that, you go integral a to b, the square root of x prime of t squared plus y prime of t squared dt. All right. Now, the last one, and depending upon who you have as your instructor, you've seen this or you haven't seen it. R is a function of theta, which means in polar. So the length of polar. Well, that becomes the integral a to b of the square root of f of theta squared plus f prime of theta squared d theta. So those are the 3 variations of arc length, finding the length of a curve. And so you should be familiar with them. Now, which one is the most important? I would say the one that's probably the best to know is the parametric, because the other 2 are really just special cases of what happens for parametric. As an example, you can think of y equals f of x. That's the parameterization t comma f of t, and then this formula goes right into that formula. And the way that you prove the formula for r equals f of theta is you first convert everything into parametric, and then wonderful cancellation happens. Okay, but which case are we in? Yeah, we're in the first case. So this is our length. So it's the square root of 1 plus f prime of x quantity squared. This is our f of x. So oftentimes we want to say, what is f prime of x? So this is a good chance for us to practice our differentiation skills. All right, f prime of x. Well, there's the 1/2. What rule do we need to take the derivative here? Product rule. All right, so the derivative of the first is 1 times the square root of x squared minus 1 plus x times the derivative of the square root of x squared minus 1. And I'll just talk through that. That's square root of x squared minus 1, and I can think of it as x squared minus 1 to the half. So the half comes down. Then it'll be x squared minus 1 to the minus a half, then times the root of the inside, which is 2x. And we'll come back and visit what that is. Minus a log. Well, the way you take the derivative of a log is you do whatever is on the inside. That goes into your denominator, x plus square root of x squared minus 1. Then upstairs, you put in, well, what's the derivative? Well, the derivative of x is 1 plus, and the square root of x squared minus 1, again, a half comes down, x squared minus 1 to the minus a half times 2x. All right, there's f prime of x. Now, currently, that does not look fun to square. So probably what should we do before we square anything? Yeah, we should work on simplifying. Now, there's some things which are really low-hanging fruit. The 2's and the halves cancel in a couple places. All right, well, what else can we do? Well, let's work on the second term for a second here. So what do we have? We have 1 plus x over the square root of x squared minus 1 divided by x plus the square root of x squared minus 1. Okay, I'm just x and then to the minus a half. Now, what can I do? Indeed, these are mysterious questions. Conjugate? Whoa, oh, that's a bold choice. Maybe, before we get to conjugate, let's get rid of the fraction within a fraction. How can I do that? Okay, I can get a common denominator. All right, so for instance, here, I can write a square root of x squared minus 1, square root of x squared minus 1, right? Square root of x squared minus 1 over square root of x squared minus 1 is 1. And if we do that, we have the square root of x squared minus 1 plus x. That's this part right here. We have the x plus the square root of x squared minus 1. That's that part right there. And then this is a 1 over square root of x squared minus 1. Okay? It's all true. I haven't lied to you. What happens here? It's 1. So the second term, this term here, which looks terrible, gets to something which looks slightly less terrible. Okay, good. We're making progress. Now, update. What do we have? F prime of x is 1/2 square root of x squared minus 1 from this part, plus, what do we have here? We have an x and another x, which makes it an x squared, divided by the square root of x squared minus 1, plus 1 over the square root of x squared minus 1. Oh, not plus, sorry, minus. Got to pay attention. Well, that's 1/2 of the square root of x squared minus 1 plus x squared minus 1 over the square root of x squared minus 1, because these have common denominator. But what does this second term become? What does it become? The square root of x squared minus 1. Because if you look, they're both x squared minus 1, so it's just the upstairs is to the 1 power, the downstairs is to the half power. So I have a half of square root of x squared minus 1 plus square root of x squared minus 1. If I put that all together, what do we end up with? The square root of x squared minus 1. Okay.
Where did you get the negative to the positive on your f prime of x?
What, here?
Yeah.
Well, that's because I accidentally put plus when it should have been a minus. Because I wasn't being careful. You got to be careful. Okay. I don't want you to be nervous. There's nothing on the test that's a differentiation that's this hard. We work hard on the practice so that when we get to the test, it's easy. Now, are we done? No. All we've done is figure out how to write that. So, now we're ready to do the real problem. So the length is the integral a to b 1 to 5 of the square root of 1 plus the derivative square root of x squared minus 1 squared. Well, now we've got to integrate that. What happens when we square the square root of x squared minus 1? It becomes x squared minus 1. And then what happens? The plus 1 and the minus 1 cancel. That's good news for us. Then you have the square root of x squared, also known as x. So you see, the price of having an easy integral here was having a terrible function there. On the other hand, you can have a really easy function here and a terrible integral down there. So, well, it just depends where do you want to pay the price. All right, integral of x? 1/2 x squared. Evaluate that from 1 to 5. So we're going to end up with 25 halves minus 1/2. What does that become? 12. And now we're done. Good. All right. Number 5. Set up, but do not evaluate, an integral to find the surface area when y equals e to the x for 0 less than or equal to x less than or equal to 1 is spun around the line y equals x. So let's see what's happening here. We have the curve y equals e to the x, and we know what that looks like. At 0, e to the 0 is 1, and then it's going to move up. So this is our curve y equals e to the x. And now we're going to spin, and of course we should have paused. What's our key word here? Yeah, surface area. We'll come back to that in a second. And we're going to spin not around an axis, but around this line. Y equals x. Now you might ask the question, are we allowed to spin around the line y equals x? And the answer is yes, we can spin around any line we want. Of course, we have to figure out what does that do to our formulas. So this is why it's good to memorize the generic formula. So let's talk about the generic formula for surface area. So for surface area, we add up, okay, then what do we have? 2 pi, good. And then? Yeah, the radius. This is the part that's kind of interesting. It's what goes into the box. And this can vary, so you have to think about that. We'll think about that. But then what's the other part? Length. All right. And that's it. That's the whole formula. So if you can remember that, you're good to go. So how do we think about it? Well, first off, we'll think about our various pieces. The way we think about it is we just take a little tiny piece, and that's our part that we spin it. So let's see. Let's work through it. What are the bounds going to be? 0 to 1. Now, the 2 pi, that's a number, so it's just 2 pi. Now we come to the interesting part, which is the radius. So the way you think about the radius is you say, how far is my little piece from where I'm spinning? So the question is, how far is that away? So what we need to know is what's the distance from this point to this line, y equals x. There's actually a note here. We probably should have read it. The distance from a point, AB, to the line, y equals x, excuse me, is 1 over root 2 times the absolute value of a minus b. Okay, we can use the note. So we have to think, how do we use the note? Well, let's talk about this point. This is the point, x comma e to the x. So I can think of this as my a comma b. So according to this distance, which is our radius, the distance to where you spin, is what? Well, 1 over root 2, absolute value of x minus e to the x. Okay, so that's our radius. Now we want to clean up. We don't want absolute value. Can we get rid of our absolute value, and how do we do it?
Square it.
Well, we don't want to square it because we just want radius. We don't want radius squared. So the way you get rid of an absolute value is you say, is the inside positive? If it's positive, you can drop it. If the inside is negative, what do? You negate it to make it positive. So which one's bigger here? X or e to the x if I'm over in that region? E to the x is bigger. So this is actually negative on the inside currently. So we say, look, I can just drop the absolute value if I write it as e to the x minus x. So my radius is 1 over root 2 e to the x minus x. Okay, now what do we do for the length? Well, length, we use our length formula. And this is y equals a function of x. So the length will be 1 plus f prime of x, derivative of e to the x, e to the x, and we square that, that becomes e to the 2x dx. So this is our length. Now, what's the next thing to do? Yes, that's right. We don't need to do anything else. That's the answer. Why? Because this is probably the most beautiful words that a student sees on the exam. Do not evaluate. So, if you see those words, do not evaluate, you should not evaluate. Now, it might be that you could evaluate, but oftentimes it's because you can't evaluate. Okay, so this is just to demonstrate the flexibility of memorizing the generic formulas and not saying, well, it's 2 pi x or it's f of x. No. Just what does everything mean? What does everything mean? That's what you should pay attention to. There.
I had a question. So for the absolute value,
Right?
like say if I was on the exam, would we leave it in that form, or would you want us to change it to be e to the x minus x?
I would say that you probably would be fine leaving it in that form because it is a correct setup in terms of leaving it as the absolute value. Other questions? You might be wondering, are there any questions on the exam where it just says set up? Yes. There will be. So you should be good at setting things up. And even if there weren't questions that ask you just set up, you should still be good at setting things up. Because if you don't have the correct setup, then all the computations after that will not get you very many points. All right, now on to physics. Good physics. There's an empty bucket that weighs 20 pounds and is connected by a chain that weighs 1 pound per foot to a pulley 10 feet off the ground. So let's see. We should probably be drawing some pictures here. So this is a bucket. You can tell it's a bucket because it says bucket. Then there's a chain. And there's some sort of system here. Okay, so this is 10 feet. All right. And as you turn on a machine that will lift the bucket up to the pulley. So the bucket's going to be moved up 10 feet. A heavy rainstorm starts, which causes the bucket to start filling with water at a constant rate. Now, given that when the bucket stops at the height of 10 feet, that the machine has a readout indicating that 450 foot-pounds of work was done, then find the amount of water that is in the bucket at that time. So this is sort of a different problem. See, here, we don't have to find the work. Or if we did, it would be like, there it is. We found it. So it's not looking for the work. It's saying, okay, some work was done, and what did you have to do to get to that answer? So we have to figure out what happened with the problem. So, all right. So we think about our work. Now there's a couple of variations of work, but basically the way you do work is you do the following. Work is you add up, which means there's an integral, and there's two pieces, a force and a distance. So that's what we need to figure out. So we need to figure out what's our force and what's our distance. Now, when we're going to start a problem, particularly one that involves applications like this, one of the things we should do is decide on coordinates. So, where should we put 0 at? Bottom? Okay. So here is 0. What is this side up here? 10? Perfectly fine. All right. So there we have a coordinate system. We know where 0 is. We know which way up is. Now, when we think of force, really that's another word here for like weight. You can think of it as pounds. So we need to figure out how heavy something is. The distance, the way we think of these problems is we're going to move it a little tiny bit. So it's like you have your bucket at a certain level, and then you just like barely up. So we're thinking of it as a small change in where it was. So this here will become a dy. All right, so we're making progress. So let's think about our weight. So what contributes to our weight? The bucket, the chain, and the water. So there's 3 things contributing to our weight. So we should figure this out. So we have the following. The bucket, initially, so I'll do our force at a particular value y. So how much does the bucket weigh? 20 pounds. Okay, and that doesn't change. The weight of the bucket doesn't change. Now the weight of the water changes, but the weight of the bucket doesn't. So that's always 20. How much weight will the chain be? It'll be 10 minus y. Now, why is that? Well, if you're at a particular height y here, the amount of chain is the difference between 10 and y. So that's how much chain is left that you have to pull up, 10 minus y. Okay, so we have our bucket weight. We have our water weight. Sorry, that's our chain weight. We need to do our water weight. Okay, how do we compute that? Well, we need to figure out what's happening here. The water is coming into the bucket. So there's a key word, constant rate. All right. So we should think of it. Okay, how much water is in the bucket initially? 0. How much water is in the bucket at the top? We don't know, but let's give it a name. What do you want to call it? Well, not y, because y is a variable. X? X? What? K? I don't know. Okay, X, all right. X equals weight of water at the end. Okay, so what we know is when y equals 0, our weight is 0. When y equals 10, our weight is x. So the question is, how much is our weight at any time in between? So we could, of course, graph this. If we put here y and we put here weight, we're at 0, 0. And then over here we're at 10x. Whatever that value for x is, we don't know. So that's what the weight of the water should be doing. It should be going in that kind of a line here. So what? Well, x minus y at y equals 0 would have value x. What's the slope of this line? X over 10, right? Because you went up by x, you went over by 10. What's the y-intercept? 0. So we now have the slope is x over 10. The y-intercept is 0. So that says that the weight is going to be the slope times y. X over 10 times y. So, plus x over 10 y. So that's the water. All right. So that's our force at any given time. Okay, we've now done most of the hard work, which is good because we're running out of space on the page. So let's put it together. So we have the work is 450. So 450 is equal to integral from 0 to 10. The force, which is 20, plus 10 minus y, plus x over 10y. All right. And then the distance, dy. So x, here we run into the challenge. We have to resist the urge to think of that as the variable. It's just some unknown. Now we need to integrate. Well, we can do a little bit of work here before we integrate. Notice that the 20 and the 10 becomes 30. And then we have plus x over 10 minus 1 times y. So we could combine things together if we wanted to. All right, let's integrate these. What's the integral of 30? 30y. Okay. This x over 10 minus 1, what do we do with that? It's a constant, so it just comes down. Integral of y? Yeah, y squared over 2. And now we need to evaluate this from 0 up to 10. So, plug things in. Nice thing is when you plug in 0, you get 0, because you get y and 0, y squared is 0. When you plug in 10, you're going to get 300 plus x over 10 minus 1, and 100 over 2 is 50. So, 450 equals 300 plus this quantity x over 10 minus 1 times 50. What do you do next? Yeah, we could subtract 300. And if we did that, we get that 150 equals x over 10 minus 1 times 50. Now what? Divide by 50. Then you get that 3 is equal to x over 10 minus 1. Add 1. 4 equals x over 10. Multiply by 10. So we end up with x equals 40 pounds. And that's how much water got into the bucket. You might think that's a heavy rainstorm, but in math, there's many interesting phenomenon that would never happen in real life. Well, I've been in some pretty heavy rainstorms, and it might be a very slow-moving chain. So, all right, that's the answer. Okay. Number 7. A tank is formed by taking the curve y equals x squared, where x goes between 0 and square root of 7, and spinning it around the y-axis, where all distances are measured in feet. So let's see. So we have this y equals x squared. Here is square root of 7. That's an interesting choice to make. And we're spinning it. So there's our tank. Now, the tank is completely full of a liquid which has a density of 50 pounds per cubic foot. Determine the work to pump 1,000 pi pounds of the liquid to the top of the tank. So in other words, the top of the tank is to the rim. Okay, so this is a pumping problem. All right, well that's not so bad. let's talk about pumping problems for a second here. First off, we'll add some liquid to our tank here. Okay, good. Now our tank is full of liquid. So, how do we do pumping? Well, when you want to find the work for that type of problem, you add up, and it's still force times distance, but here it's a little bit more interesting because the distance is not going to be that d something term. So we would like to put the distance term first. Then we have the density term. And then we have a little volume. So we're going to do an area and a height. So when I talk about area here, this is the area of a cross section. So that's what we mean by an area. All right. So most of these aren't so bad. Now, we already, in some sense, have a coordinate system built into the problem because it talks about, the y equals x squared, x goes between 0 and 7. So why don't we just use the coordinate system that's given to us? So where is the top of this tank? Yeah, it's at 7. Okay. So what will the distance be? So I want to imagine I'm pumping here. And so the idea is I'm just going to pump out a little tiny slice. It's like I'm taking a small sliver of water. And I'm going to take this small sliver of water and move it out. So if this is at height y, what's the distance I have to go? 7 minus y. What's the density? 50. Okay, that's not so bad. Now, the area of a cross section. Well, let's think about it. What do our cross sections look like? They're circles. Okay, well that's good. So a cross section would look like pi, and then you'd have to have radius. Let's think about that. So, what is, this is really going to make this picture work hard. What is our radius here? Well, remember y equals x squared. The radius would be, what is x? So what is x? Square root of y. When I come over here, I want to take pi radius squared. So what goes there? Well, I need to know, no. Pi y. What's the height? dy. So the area times the height, that's the volume of that little tiny slice. Okay, we're looking pretty good. What don't we know yet? Bounds. Okay, where does the bounds go? I agree with the 7. Let's be careful here. Are we emptying the tank?
No.
We don't know yet, right? What are we asked to do? We're asked to pump that much water out. That's how much water we should pump out. Now the question is, what does that correspond to? Does that correspond to the whole tank? Does that correspond to just the top foot? The top 2 feet? Okay, well, we always will go to the top of where the water level is. So the upper bound is not so bad. So the question is, how far down do we have to pump to get out to 1,000 pi pounds? Okay, well, let's think about this. So there's a little bit of work we have to do before we can do our work problem here. So let's see. Well, we know that our density is 50 pounds per cubic foot. So if we've got to pump out 1,000 pi pounds, quiet. Okay, so if we've got to pump out 1,000 pi pounds and it's 50 pounds per cubic foot, how many cubic feet do we need to pump out? Sorry, what was it? Okay, so we know we need to pump out 1,000 pi pounds. Oops, pounds. And we know it's 50 pounds per cubic feet. So the question is, how many cubic feet? So the question is, what do you have to multiply by 50 to get to 1,000 pi? Well, definitely we need to pi, and we need 20 pi. So that's how many cubic feet we need to pump out. Okay, so does that mean 20 pi is here? No, of course, that's ridiculous. 20 pi is a big number, much bigger than 7. Okay, so how do we use that information to figure out where our lower bound is? Use the area of our cross-section to do what?
Well, you use that volume total, and then find your height down. You take 7 minus the height down.
Okay, so this is a volume that we're after. So now we're going to get to do a volume problem inside our work problem. So we want our volume, which is equal to 20 pi. So we got to find the volume, but we're going to think of going from volume from top down. So it's got to equal the integral from some number, I'll call it a, up to 7. Now we've got to figure out, how do we compute the volume of this shape? Well, how do you compute the volume here? What's the right tool?
Area of our cross-section.
Well, area of our cross-sections, yes. What's the area of our cross-sections? If only we had the answer to such a thing. Yeah, it's pi y. So that's we need to get 20 pi cubic feet. So we need to figure out at what point, what's the value for a, where integral from a to 7 of pi y gives us 20 pi. Now the nice thing is we can actually cancel the y straight off. So, the pi straight off. So, okay, let's integrate this. If I integrate y, that's a half y squared. Evaluate that from a to 7, which is 1/2 times 49 minus a squared. And remember, what do we want that to equal? We want that to equal 20. Okay, so let's start. Clear off the half. We need 49 minus a squared to equal 40. So what does that tell us? Yeah, a squared is 9, or a equals 3. And you might say, well, shouldn't it be plus or minus? But we have the problem that tells us the shape. It's not going to have negative value. So that work was to get us to here. So we can put a 3. Okay, now we're ready to keep going. All right, so back to work, as they say. We have the 50 and the pi. That's a constant. That can come out. So 50 pi, integral 3 to 7. Then you can distribute the y through. So 7y minus y squared dy. So 50 pi, and now we integrate. That'll be 7/2 y squared minus 1/3 y cubed. Evaluate that from 3 to 7, which is 50 pi times, well, you get 7/2 times 7 squared minus 1/3 times 7 cubed. Subtract 7/2 times 3 squared minus 1/3 times 3 cubed. And now, what do we do? Yeah, we're okay. That's the answer. Now you might say, well, can we go farther? Well, of course, because as we all know, 7 cubed is 343. But do we really gain anything from that? I don't know. So we'll just leave it there. All right, good. Whew. Good times, good times. I was kind of sad we didn't put this one on the exam. I thought it would have been fun. Oh well. Hopefully you like the one that's on the exam. If there is one of those. Who knows? All right, number 8. Given that a rod has the shape 0 less than or equal to x less than or equal to 1 with density delta x equals 2 plus 2x over 1 plus x squared, determine the center of mass of the rod. All right. So we have our rod, and it's not so hard to, we think of our rod as basically one-dimensional. So we go from 0 to 1. So what's the key word here, or the key phrase? Center of mass. So whenever you see a center of mass problem, you start looking at various things. Now this is a center of mass for a one-dimensional shape. We can also do center of mass for two-dimensional shapes, so be ready to do either one. Now for two-dimensional shapes, something that we'll often see is symmetry. So learn to look for symmetry. If we don't have symmetry, well, we've got to go through and do each part. So the center of mass, we denote that by x bar. It's the ratio of two things. What goes downstairs? Yeah, the total mass. What goes upstairs? The moment. Now, the moment has various notations depending upon what setting you're in. When we're doing something one-dimensional, we tend to denote that with a little subscript 0. Just means 0 there for the origin. If it's two-dimensional, we have moment with respect to the x-axis, which is m sub x, moment with respect to the y-axis, which is m sub y. All right. So, let's see. Where do we go from here? Well, we've got to compute these things. So let's talk about mass. How do mass problems work? Well, if you hang out in Professor Mayhook's class, it'll be like, oh, mass is the integral of dm. Now, dm is just a fancy way of saying your little bits of mass. The way I like to think about it is I like to do mass is your density, and then it depends on your problem, but here, in one dimensions, it's your length. Now, in two dimensions, it'll be your area, which is like height times width. But one dimension's length. So your length is your dx. Our density is our density function, which is over here. 2 plus 2x over 1 plus x squared. And the integral from a to b, well, we go from 0 to 1. So what we have is we need to integrate from 0 to 1 of 2 plus 2x over 1 plus x squared, which we can write as 2 over 1 plus x squared plus 2x over 1 plus x squared dx. Well, what's the integral of 2 over 1 plus x squared? 2 arc tangent x. What's the integral of 2x over 1 plus x squared? ln of 1 plus x squared. Evaluate 0 to 1. Now the nice thing is when we plug in 0, arctangent of 0 is 0, natural log of 1 is 0, so we just need to plug in 1. Arctangent of 1, pi over 4. Double that is pi over 2. So we get pi over 2, and then we have natural log of 1 plus 1, which is natural log of 2. And that is half of our answer. That's our mass. Okay. Well, let's do the other half. Take a moment here. Now, the way I like to think about moment is really there's just one extra thing, which is you can think of it as distance or you can think of it as location. Whatever way helps you cope better and sleep at night. Although I'm guessing not many of you lie in bed thinking about, should I think of it about distance or should I think of it about as location? So, but if you find yourself in that situation, the answer is yes. All right. So let's go through and figure out what does the pieces become. Well, actually almost all of it's the same. The density is the same, The length is the same. What does this become? It becomes x in the one-dimensional setting. So it's the integral from 0 to 1 of x times 2 plus 2x over 1 plus x squared dx. Well, that's 0 to 1 of 2x plus 2x squared over 1 plus x squared. Now we have to think about how to integrate this. And, well, it looks like it's going to be something fancy, but it's actually not so bad. So the first part's actually easy. The 2x over 1 plus x squared, we're okay with that. Now the rest of it, that 2x squared over 1 plus x squared, we might think, you know, the 2x squared's really close to something that looks like x squared plus 1. In fact, what am I missing to make 2x squared look like x squared plus 1? If I were to add a 2, I'd be like, yeah, that's really cool. But I can't just arbitrarily add a 2, but what can I do? And then subtract the 2. So this becomes integral 0 to 1 of 2x over 1 plus x squared. And then if we think of our first piece, that'll be plus 2, then minus 2 over 1 plus x squared. And now we're ready to integrate. So, in fact, most of these terms are the same. It's the natural log of 1 plus x squared. The only thing that's different here is the 2. That becomes 2x, and then minus 2 arctangent x. And evaluate 0 to 1. Again, the good news, if you plug in 0, you get 0. So if you plug in 1, we get natural log of 2 plus 2, then minus pi over 2. Now, that is also not our answer, but now we're ready to write our answer down. So our center of mass, take our moment, natural log of 2 plus 2 minus pi over 2, and we divide that by our mass, pi over 2 plus natural log of 2. Okay, now what? Yeah, we're done. There's not really much you can do with that. If you really wanted to, you can multiply top and bottom by 2 to get rid of your fractions. So you could, for instance, if you wanted to, this is the same as natural log of 4 plus 4 minus pi over natural log of 4 plus pi. All right. Now, it's not so clear how to do it here, but whenever you do a center of mass problem, what should you kind of check in the back of your head? Does it make sense? Is your answer reasonable? Now, what does that mean? Well, if we had done our center of mass problem and discovered that our center of mass was over here, what should we do? Yeah, you should check your work. A lot of people will be like, huh, well, that's interesting. Move on. No, it's not interesting. It's wrong. So, don't move on. I know you're like, but I can drop 4. Don't drop those. Save your drops for the good ones. All right. No, the real thing is save your drops for the final. Okay, oh, it looks like we get to do a mass problem here. Let R be the circle of radius 2 centered at the origin. Given that R has density, density of x is the absolute value of x cubed, then determine the mass of your region. All right, so this is kind of an interesting shape. It's a circle of radius 2 centered at the origin, which means it looks like a circle. And the density it's not a constant density. Well, what do we see about our density? Where is it dense? Yeah, it's dense the further out you are from the origin. So at the origin, it's very sparse, and then as we come out to the sides, it gets very dense. So the density happens towards the sides. Now, if we were asked to do a center of mass for this problem, what's the answer? Yeah, 0, 0. We don't even have to think about the center of mass here. Why can we get that the center of mass has to be at 0, 0 right away? Symmetry. Okay, and what type of symmetry? Well, it's symmetrical with respect to the y-axis and symmetrical with respect to the x-axis. Wherever you see a line of symmetry, your center of mass has to be on that line of symmetry. Is it symmetrical with respect to, say, the line y equals x? Is it? Is it? The density is not symmetric. See, if you flipped, this dense part would shoot up here to a not dense part. So it's not symmetrical with respect to the line y equals x. The shape is symmetrical, but not the density. So be a little bit careful. Usually there'll be some type of symmetry if you see a two-dimensional mass problem. But when we talk about symmetry, we're looking for both the shape and the density. Okay, but we're not doing center of mass here. We're just doing mass. So how do we find mass? Well, mass is we add up the little pieces of mass. See, really, whenever we say mass, we're really, or whatever it is, volume, surface area, we're saying, well, the total of it is found by adding up the little pieces of it. Okay, so where are the little pieces coming from? Well, it's going to be density times area, which I'll think of as a height and a width. Really, density times area is what it comes down to. Okay, so, well, let's think about things. Now, one of the things that we can do to simplify is to use some symmetry. So, here's something that we can do to make our life simpler. We can just focus on just that piece right there. In other words, in the first quadrant. Why? Well, if I work in the first quadrant, what do I need to do to get the total? Times 4, because everything else will have the same amount by our symmetry. Okay, so let's just do that. So we're going to do 4. Where do we go between? 0 to 2. All right, what's our density? Yeah, see, here's the advantage of working the first quadrant. If we work over everything, we still need the absolute value of x. But if we work just in the first quadrant, we can drop the absolute value signs, so it becomes x cubed. All right, now, what else do we have? The height. Okay, so we're thinking about a little tiny rectangle. So this curve is part of the circle. Well, we didn't actually write down the formula for it. It's x squared plus y squared equals 4. What's the height? The square root of 4 minus x squared. What's the width? Dx. All right. So that's what we have to do to find the mass, and we'll do that mass. Before I continue on with the problem, I do just want to make a comment that one of the things that we often do, and it seems like we always save this for exams, is we change our density from functions of x to functions of y. Does it really change anything? No. It's still the same basic formulas. It's still density, height, and width. But now it's your height would be your dy, your width would be some function of x, some function of y, and your density will be whatever it is. So be adaptable and be ready to handle any situation you're in. Okay, how do you integrate something like x cubed times the square root of 4 minus x squared? We can do u substitution, because you could probably also do trig substitution, but our goal is not to do anything that's fancy. What's our substitution that we can do? Yeah, let's do 4 minus x squared and see how far we get. If u equals 4 minus x squared, what would du become? Negative 2x dx. Now, we can actually, because we have a 4 here, what we can do is, before we get too far, and we can do 2 integral 0 to 2, and I can put a 2x times an x squared. So I'm putting a 2 inside, and I'm breaking the x cubed up as x times x squared. Square root of 4 minus x squared dx. Okay, so that'll help us. So let's see what the substitution gives then. 2, the 2x times dx, what will that do? 2x dx becomes negative du. So there's a negative coming from here. Negative du. The square root of 4 minus x squared. Yeah, square root of u. In calculus, we write that as u to the half. What do we do with the x squared? Yeah, we can use our substitution. X squared is 4 minus u. Anything else we need to do? Bounds. Yeah, let's not forget our bounds. Now, the original bounds were from 0 to 2. When x equals 0, what does u equal? 4. When x equals 2, what does u equal? 0. Well, that's weird. I don't like that order. Oh, yeah. Let's switch them and get rid of that negative. Then we'll feel better about two things. So 2 integral 0 to 4. What do we do with this 4 minus u times u to the half? Distribute through. So we get 4 u to the half minus u to the 3 halves du. Good. Now, nothing's too bad about that. That's something we can integrate. All right. So that's 2. What's the integral of 4 times u to the half? So u to the 3 halves, and then you put a 2/3 down in front, so that'll give us 8/3. And then, integral of u to the 3 halves? Yeah, so u to the 5 halves, and then you get a 2/5. From 0 to 4. And the nice thing is you plug in 0, you get 0. So we can plug in 4. So let's see, we get 2, 8/3. And 4 to the 3 halves? 8. Minus 2/5. 4 to the 5 halves? 32. All right. Good. You're getting good at this, you know. It's, in the old days, I used to be like, aha, now it's like 2 to the 5th. No, 4 to the 5th is 1,024. And now you're just like, well, all right. That's okay. All right, 8 times 8 is 64. 2 times 32 is 64. So there's actually 64s in both. I can pull it out. So I pull the 64 out in front. Times 2 is 128. Then you get a third minus a fifth. What's a third minus a fifth? Yeah, so you can think of it, common denominator is 15. So 5/15 minus 3/15, which is 2/15, times 128. Gives you 256/15. And that's our answer. That's not so bad. And amazingly, it's a problem with the circle, and pi never showed up as the answer. Well, sometimes that happens. That's just the way it is. All right. Now we're moving into the sort of third phase. So there's sort of 3 phases. Oh, there's a question. On the last problem, yes. What's your question? I'm sorry, where I got the where? Okay, so where did this 4 minus u come from? Is the question. Now, the answer is, whenever you do a u substitution, and this applies to all integration problems where you do u substitution, is if you have your original variable as x, everything needs to be replaced by the new variable. And you might say, okay, well, what does that include? Well, there's secretly an x on your bounds. X equals 0 to x equals 2. There's this 2x in the dx. That became part of the du. There's the square root of 4 minus x squared. That became the square root of u. Then there was this piece. We have to change it. It must change. Because you can't mix x's and u's. Everything has to convert over. So how do we change it? Well, for anything that doesn't come out otherwise, you go back to your relationship. Our relationship is u equals 4 minus x squared. You say, okay, well, whoa, x squared, that's pretty promising. You solve this for x squared, and you get 4 minus u. So I can replace the x squared by 4 minus u. So that's where it came from. All right. So there are sort of 3 phases to what we talked about since the last exam. So the first phase was geometry. So that's your area, your surface area, your length, your volumes. Okay, so that was phase 1. Phase 2 was physics. That's your work, your force, your mass, your center of mass. Phase 3 is your parametric curves and polar coordinates. So now we're into our phase 3. All right, find the tangent lines at all points where the parametric curve x of t equals t cubed minus t plus 1 and y of t equals 3t cubed plus t squared plus 6 intersects the line y equals 3x plus 1. So, well, we know a couple things. We need to find tangent lines. So that's one key word. We know we're parametric because it tells us it's parametric. So that's something good to know. So what do we need to start? I guess that's my question for you. Where should we start on this problem? Okay, so if we're after tangent lines, one of the things we need to know is we need to know point and slope. Now, for point, that's not so bad. You take your x, t cubed minus t plus 1, and your y, 3t cubed plus t squared plus 6. And sometimes we actually write our parametric curves this way. The x coordinate is this, the y coordinate is that. You plug in a value for t, life is good. You need your slope. Slope, that's your change in y over change in x. So change in y, that's y prime of t. Change in x is x prime of t. So what you do is you go through and you say, all right, what is the derivative of y prime? So come to y, take that derivative. What's our derivative? 9t squared plus 2t. Go to x. What's the derivative of x? 3t squared minus 1. Now, the good news is, you give me any value for t, I plug it in, I get a point. I plug it in, I get a slope. Slope and point gives me line. Life is good. So what do we need to finish up? Yeah, we need to find the right values for t, because it didn't tell us at this t or at that t. It said, oh, where something happens. So, where we intersect a particular line. So now we have this sort of second puzzle. This is one of those problems within a problem, which is great. All right, good. So, let's deal with this problem. We want to intersect the line y equals 3x plus 1. Now, at first it might seem like this is going to take a lot of time. We just got to guess and check, and maybe we'll get lucky. But we don't want to guess and check. We want to be sort of systematic. So what can we do now to figure out what the right t is? Well, we don't want to set our slope equal to 3, because that would find where we're parallel to this line, not where we intersect this line. Yeah, so we're looking for when is this relationship satisfied. So we say, look, there's our x, so we put that in for x. There's our y, we'll put that in for y. And now we'll figure out for which t does this work. So we have 3t cubed plus t squared plus 6, that's our y, has to equal 3 times t cubed minus t plus 1 plus 1. So we start working this formula, 3t cubed plus t squared plus 6, distribute the 3 through. 3t cubed minus 3t plus 3 plus 1. Well, let's move everything over. What happens to our t cubed terms? Cancel, almost as if we were anticipating that. Hopefully we did. Hopefully we're going to get something that can work. So the t squared, there's just one. What do we have for our t terms? What do we have? plus 3t, and then plus 2 equals 0. All right, well, that says that has to be true in order for us to intersect the line y equals 3x plus 1. Now we've got to figure out, when is this true? Well, what can we do here? Factor. Oh, I hope it factors. Does it? Yeah. Well, you should be suspicious. Things should work out fairly nicely. Okay, so what does that say about t? -1 and -2. Now notice, that's not our answer, but that tells us the times. And that's what we were missing. We needed to know the times to get our lines. So now we know there's going to be 2 different lines, one for each value of t. So at time -1, well, so we plug -1 into here. -1 cubed, -1, subtract -1, plus 1, and then plus 1 more. So the x-coordinate is 1. 3 times -1 cubed, -3, plus 1, plus 6. 4. And then our slope, so that's our point, our slope, well, 9 times -1 squared, 9, then minus 2, 2 times -1, over 3, -1 squared, minus 1. So that's 7 halves. So there's our point, our slope. So we get y minus our y value, which is 4, is equal to our slope, 7 halves, x minus our x value, which is 1. And that's one of our answers. We don't have to simplify. That's a nice form for the line. But that's not our only answer. So we have to do the other case. All right. -2. Well, this one we might have to think a little bit more. So, -2 cubed, -8 minus -2, plus 2, plus 1. -2 cubed is still -8 times 3, -24, -2 squared, plus 4, and then plus 6. Well, -8 plus 2 plus 1 is -5. -24 plus 4 plus 6 is -14. Our slope, well, 9 times -2 squared, 36. 2 times -2, minus 4. Downstairs, 3 times -2 squared, 12, minus 1. So that's 32 elevenths. So the line would be y minus our y-coordinate, minus 14 makes it plus 14, is equal to our slope, 32 elevenths, times x minus our x-coordinate. Minus 5 makes it a plus 5. And we probably wouldn't have guessed that the answer would have involved the 32 elevenths when we started. But it's good to check. All right. All right, let's do the next problem. Good. Number 11. Find the surface area when this parametric curve, t minus 2e to the 2t, 4e to the t, where t goes between 0 and log 2, is spun around the x-axis. Now, do I know what it looks like? No. They didn't provide a picture. Probably because, a picture's not going to help us very much. Now, like I said, I don't know exactly what it looks like. Well, it looks something vaguely like that. I do know for sure that it's on the positive side. So in other words, look at that 4e to the t. It's always positive. And we're going to spin it around the x-axis. All right. So that's our goal. That's what we want to find. Now, what are we going to do? Well, let's remind ourselves about surface area. Now, surface area, we have a nice generic formula. We're adding up our little pieces of surface area. And our little pieces look like 2 pi, and then there's a box. And what goes in the box? It's the radius. And this is sort of the interesting thing, because it varies a lot depending upon what you're doing. And then the other piece is length. And that's it. Because if you take a 2 pi radius and length, that finds the surface area from a little piece. All right. Well, what's the radius? If you think about it, you say, take a little tiny piece. So there's our little tiny piece. See that? It's very small. That's how you know it's little and tiny. And you say, how far is it to where we spin? Now, so what's the answer? How far is it from a little tiny piece down to where we spin? The answer is y. Now that's, of course, in terms of the coordinate. Now in terms of what goes here, we're going to use the 4e to the t. All right, so that's going to be there. Let's focus on length, because I think the length is going to be the hard part of this problem. It often is, and that's because the length is where we see the square roots coming in. So let's remind ourselves how we do length. So length, that's going to be the square root of, you take the x-coordinate, take its derivative squared, take the y-coordinate, take its derivative squared, and then you multiply it by the dt. So let's spend some time, and we really will have to spend some time making sure we got that figured out. Okay, so let's work it slowly. So again, I'm just focusing on the square root. I won't worry about the dt. So this will become the square root of the derivative of the x-coordinate, 1 minus 4e to the 2t squared. Don't forget the square. Derivative of the y-coordinate, oh, that's nice, 4e to the t squared. All right. Well, now our chance to show off our algebra. All right. We're not going to hide our algebra skills under a basket. We're going to let it shine. Square this, you get 1. Then you get the cross terms. So it's like a squared, then 2ab. So it'll be 2 times 4 is 8. There's a minus sign, so it's minus 8 e to the 2t, square the last term, plus 16 e to the 4t. Now how about this term? It's also a 16, but it's not 16 e to the 4t, it's 16 e to the 2t. Okay, now what happens here? Well, if you take a look, you might say, hey, the e to the 2t's match up, because they match up. All right, so we put them together. And what happens? Well, we get 1 plus 8e to the 2t plus 16e to the 4t. Good. Now we might say, boy, that'd be nice if it was a square, but you should not really think too long, because you say, wait a second, that's almost identical. Just that minus became a plus, and that minus is because we had a minus there. If we had a plus there, that's what we would have. That means that this is really the square root of 1 plus 4e to the 2t squared, or 1 plus 4e to the 2t. Nice. Nice. All right. Now let's put this all together. Let's put it all together and let's see what we have. So here we go. We have that our surface area, well, a to b. Now, because it's a parameterized curve, we use our parameterization times. So 0 to log 2. The 2 pi is still 2 pi. The radius, that's the y, but y becomes that 4e to the t. So 4e to the t. Now the length. Well, the length is the 1 plus 4e to the 2t. That's the square root term. Don't forget the dt. So 1 plus 4e to the 2t dt. Now it's set up. And it looks like it's something we could do. So, let's multiply this out. Let's see what we get. So we get 0 to log 2. 2 pi times 4 is 8 pi. And then there's an e to the t, multiply it through. So the first term is 8 pi e to the t. And then plus, oh, big number, 32 pi e to the 2t. Probably shouldn't have multiplied the 8 pi through, but, well, we were in a moment of passion, right? So we just went with it, dt. And these are both very straightforward things. So what do we end up with? Well, we end up with 8 pi e to the t plus 32 pi, whoops, e to the 2t, that's not e to the 2t, right? Because it's e to the t times e to the 2t. Ah, this should be a 3t. So 32 pi over 3 e to the 3t. And almost there, we were going from 0 to log 2. So, plug in log 2. Well, e to the log 2 is 2. So, times 8 pi gives us 16 pi. So that's plugging log 2 into the first term. Now, what about e to the 3 log 2? Well, little note here, e to the 3 log 2. You can move the 3 up into the exponent. That's really the same as e to the log 2 cubed, or e to the log 8, which is 8. 8 times 32, well, that's of course 256, right? Well, I think it is. Well, I'm convinced. All right, so 8 times 32, 256, pi over 3. Now that's when I plug in log 2. Don't forget, you also got to plug in 0. Well, but the nice thing is e to the 0 is 1. So you get 8 pi and subtract, plus 32 pi over 3. Now we can probably clean this up a little bit. 16 pi subtract 8 pi, that would give us 8 pi. So that's just difference there. 256 over 3 minus 32 over 3. Well, 256 minus 32 would be, what would it be? 2, 2, 4, right? Because you just 256 subtract 32. So, yep, 224 over 3. And don't forget the pi. Now, we should check, is 224 divisible by 3? And the answer is no. Now, how can we tell? Well, add the digits. 2 plus 2 plus 4 is 8. Now, if the number is divisible by 3, then the sum of the digits has to be divisible by 3. It's a nice, fun little fact you get to learn back when hopefully you were younger. You know, when you just learn fun facts for fun. Ah, it was fun to learn things just for fun. Now we feel like we're obligated to well, let's work hard and learn things. Now, 8 pi, we can make that something over 3. That's 24 pi over 3 plus 224 pi over 3, giving us a grand total of 248 pi over 3. And that's our surface area. Maybe not the nicest answer, but we've seen worse. All right, that's good. Fun problem. Good. Number 12. A wire follows a parametric curve, x of t, y of t equals sine of t, log of 1 plus t squared. I don't know what that looks like, so we'll say it looks like that. Time goes from 1 to 4. And we're told that the density at a point x of t, y of t is given by some function, delta t equals root t. So it looks like the further you go on the wire, the more dense it is. So there's more density towards the end of the wire than there is in the middle and compared to the end. So the wire grows in weight as you move along. Then set up, but do not evaluate, oh, thank goodness, an integral to compute the total mass of the wire. All right. Now, you might say, have we ever done something like this before? Kind of. We have all the pieces. And the question is, do we understand our pieces so we can put them together? And that's what we're trying to do. Can we put things together? So let's try that. So if I'm trying to find the mass, how do I find mass? Well, I add up the little pieces of mass, which is the density times whatever the appropriate thing is. So when I say the appropriate thing, if I have a one-dimensional thing like a rod or a wire, the appropriate thing to use would be a length. If I have a two-dimensional thing, the appropriate thing is the area, which is usually a length times a width, height times a width. If I have a three-dimensional thing, I should be in multivariable calculus, which is next semester. Okay, So once we have the basic understanding, it's like, oh, okay, well then there's really nothing too foreign. What should our bounds be? 1 to 4. What should our density be? Square root of t. What should our length be? Well, we used the length formula for parametric. So square root of, and then what do we do? Our x prime, derivative of sine, cosine, squared, plus, take the derivative of log of 1 plus t squared, which is, what is that? 2t over 1 plus t squared, squared, and dt. dt is part of the length formula. And now, what do we do? Yeah, that's it. It's basically a test of, do we understand the formulas and can we adapt to new situations? So there are often times when we'll say, oh, here's a couple of interesting things. Can you adapt to this new situation? All right. Number 13. Find the area of the region shaded below which lies between the curves r equals 3 and r equals secant theta plus 2 cosine theta in the first quadrant. It's a little tiny sliver. You can barely see it, but it's right there. It's this green piece right here. Now, so there's two curves. There's this curve here, and then there's this more sort of interesting curve. Let's see if we can figure out which curve is which. Which curve is the r equals 3 curve? Yeah, that's the circle one. That's not so hard to figure out. R equals a number is a circle. So r equals 3, that's this circle one, which means by process of elimination, the other one is the secant theta plus 2 cosine theta curve. Okay, so that's good news. We figured out which curve is which. What are we looking for? Area. How do we know we're looking for area? Yeah, because it says it. Find the area. It's really cool to like pick these clues up. Like, ooh, area. I have a tool for that. And we also know, it doesn't explicitly state polar, but we know it's polar. How do we know it's polar? See r's and thetas. Yeah, see r's and thetas, you know it's a polar problem. So we say, all right, we know how to do area in polar because we have a nice formula for it. Now, there's sort of two variations of area. There's the one variation, which is when you have a curve and you go straight to the origin. And in that case, your area is alpha to beta of 1/2 your, well, for lack of a better word, I'll say r squared. It's your distance out. But the other thing, which is probably the more interesting one, is if we're going between two. So we're looking for an area between two curves. So here the area, alpha to beta, 1/2, you have your outer radius squared minus your inner radius squared. In some sense, it kind of feels like the same formula as for the washer method. The only difference is instead of pi, you have a half. But it is slightly different. Of course, the processes are still the same. Which one of these two are we in? Yeah, we're in the second one. And it might help us to sort of say which one's the inside, which one's the outside. If you're not sure, you just sort of go out from the origin and say which one do you hit first and which one do you hit second. So what's our outside curve? In our case, it's the 3. It's the one that's furthest out, the circle. What's our inside curve? Not 3. Okay, yeah, all right. Secant theta plus 2 cosine theta. Okay, what's left for us to do? The bounds, all right. So what do we need to do? Well, the bounds might be given to us, and if they're not given to us, we need to figure them out. Okay, we're in the first quadrant, that's good. Okay, so we can set these equal to each other. 3 equals secant theta plus 2 cosine theta. Now, I will say that there's various things you can do. Certainly you can do things like guess and check. That works, but you have to check. You can't just guess. Another thing is you can do some algebra. Let's do algebra, because I know how much we enjoy algebra. It's a great pastime. I'm going to regret this choice, I suspect, in a minute, but that's okay. What's another way to think of secant? Yeah, 1 over cosine. So 1 over cosine plus 2 cosine, and this equals 3. So I'm going to do two things. I'm going to multiply everything by a cosine, and I'm going to bring the 3 across. So if I do that, I'll get 2 cosine squared theta. So that's because I multiplied that by a cosine. Minus 3 cosine theta, because I multiplied by a cosine the 3, and then I brought it to the other side, plus 1 equals 0. This is a quadratic in terms of cosine. Well, we'd like to solve this, and in the ideal situation, what should be true? Should factor. Does this factor? It does. How does it factor? 2 cosine theta minus 1 and cosine theta minus 1. You can check 2 cosine squared theta minus 2 cosine theta minus cosine theta. That's the minus 3 cosine theta and then the plus 1. So what does that tell us about cosine theta? 1/2 or 1. When do I get cosine theta equal 1? 0. Which I probably could have guessed. When does cosine theta equal 1/2? It's one of the angles we know, right? So it's going to be one of those pi over 6 or pi over 3. And if you're not sure, look at the angle. Does it look like it's more 60 degrees, or does it look like it's more 30 degrees? It's definitely not, it's closer to 90 than it is to 0. So that's a 60 degree angle, of course, what we would call pi over 3. All right, good. Well, now we just have to do this integral. And unfortunately, I left myself almost no space to do it. Well, that's how I screw up sometimes. Okay, the 1/2, we'll pull that out for now. Square things, we get 9 minus, put a parenthesis there to make sure I don't lose anything. Square secant squared. What's the next term? Before times secant times cosine, also known as 4, plus 4 cosine squared. Now, are we okay with secant squared? Yeah, it's actually a great thing for us to use. Secant squared is a wonderful thing to integrate. So we're happy with that one. The 4 we're fine with. The 4 cosine squared, what do we do there? Oh, wow, you guys you're on that ball. You're going to be ready for any power reduction on that test. Now we just got to hope we put a lot of it on there. Cosine squared is 1 plus cosine 2 theta over 2. Okay, now let's be really careful here, because I don't have very much space left. Equals, put it over here, 1/2 integral 0 to pi over 3. Let's pull out the constants, put them all together. I have a 4 here. I also have a 4 times 1/2, which gets me up to what? Yeah, that'll be 2. Plus 4 makes 6. And then that's being subtracted from 9. So I'm at 3. I have a minus secant squared. And what else do I have? Two cosine 2 theta. Added or subtracted? Subtracted. Okay. Well, good news, we can actually do those things. 1/2 integral of 3. 3 theta. Integral of secant squared. Tangent. Integral of 2 cosine 2 theta. Sine 2 theta. Evaluate that from 0 to pi over 3. Okay. The nice thing is when you plug in 0, all these terms become 0. Tangent of 0 is 0. Sine of 0 is 0. So that's good news. So we need to plug in pi over 3. So what do we have? We have 1/2. 3 times pi over 3? Pi. Tangent of pi over 3? Wait, what is it? Root 3. Tangent of pi over 6 is root 3 over 3. Sine of 2 pi over 3. Root 3 over 2. So we could actually put these root 3's together, and if we wanted to, we can even pull out a half again. So if I pull out a half, that'll leave me with 1/4. So I pull out a half. When I pull a half out of the pi, what will that give me? 2 pi. And then I'll be left with 2 root 3 minus root 3, which is minus 3 root 3. And that is that area right there. 1/4 of 2 pi minus 3 root 3. Okay, now, on a side note, I have shown you very poor space skills here. When you're on an exam, your work should like flow. It shouldn't be like here, and then there, then up there. That's a bad way to put your work. Because when people are grading, they're not going to spend 45 minutes pondering your masterful penmanship. They're going to look at it for about 15 seconds and see how much can I follow. And if it's organized, they can follow a lot better. And they can be like, okay, I can see that was a small mistake. But if it's disorganized, they can't tell the difference between a small mistake and a big mistake. Be organized. The other thing that it helps is it helps you when you go back and check your work. Because it's much easier to follow a clean argument than to follow something which is a little bit messy. Okay, number 14, a matching problem. Well, maybe. For each of the following 3 curves in polar coordinates, so these are curves in polar coordinates, select the picture which corresponds to the curve. So I've got three curves, and I've got 3 pictures. Okay, what do we do? Well, we've got to start thinking about it. Now, when you're working with these curves, and it doesn't matter whether it's these polar curves, it could be parametric curves, whatever you have, if you're not sure what to do, just start thinking about some basic things like where am I at time 0 or at angle 0? What's happening to me? What are some basic properties I have? So let's think about the various things. Now, one of the things you can do to help you is you can say, look, if I'm not good with plotting in polar, let me just think of this as plotting if it was a theta and r. So for instance, 2 plus cosine theta, that says take your cosine curve but shift it up. So it would look like this. What are some things we can tell about this curve? Yeah, so pi is a low point. Where are we at pi? 1. So that says if I'm looking in the direction of pi, which is in this direction here, I need to find some place where I'm distance 1 away. So that says I can eliminate the bottom one here, because there's nothing where I start looking direction pi and move in 1. So I can eliminate 1. So it's either 2 or 3. What are some other things we can see? Sorry, what? It goes up to 3. In what direction? Right, in the positive, in 0, which is the positive x direction. It's at 3. So that says I should only go distance 1 in the negative x direction, distance 3 in the positive x direction. Well, what do you notice about this curve? You're going equal in both directions. This one looks closer, and this one looks further. So we can eliminate 1 and 2. So it's sort of like the SATs. If you don't know what it is, eliminate things. And then you must say, well, whatever's not eliminated, I'll guess. Well, don't guess. There's one other thing we can say. So the correct answer for A is 3. Another thing you should look at is do I ever hit 0? 0 is an important point in polar coordinates. Look here. Do you ever go to 0? No, you're always staying away. So if I look at these three curves, I can say, well, look, only one of them never goes to 0, so it has to be 3 is the right answer. All right. Well, that's that one. Now, r equals 1 plus 2 cosine theta. Now, you might be thinking, I only have to choose between these two curves. Be careful. Because maybe there's an expression which says, lo and behold, if you modify this expression, it could be the same curve. So don't take it for granted. It's like, aha, I can eliminate this one from the consideration for the rest. All right. Well, let's think about it. What are some properties which should be true about 1 plus 2 cosine theta? Okay, so, well, if I were to sketch 1 plus 2 cosine theta, what would it look like? It peaks at height 3. How low can it get? It actually goes down. Then it comes back up. So what should we be looking for? We should be looking for something that's far away. We can even start to sort of sketch it. It should be far away. And then it should come into 0 right here. And then when you see a negative, it should do a little loop back to 0. And then it should just be getting bigger. So this shape tells us kind of what we should be looking for. I wonder if there's anything that matches that. Well, 1 looks pretty close, so I'll go with 1. There are some other things. Again, just think about, okay, where should I be if I look in 0? If I look in the direction 0, I should be at 3. Where should I be if I'm looking in the direction pi? Well, this says -1, so I should be back here. So I should be hitting both 1 and 3 on the positive x-axis. You'll notice at this point it only hits 1 point on the positive x-axis. So there's clues. So pick some points, work the clues. All right, last one. C, 1 plus cosine 2 theta. We're probably going to guess 2, right? Yeah. Let's put 2 in, but let's see if we can convince ourselves that it should be 2. Well, what are some things we should be checking? Well, yeah, let's check where we are at various angles. For instance, where are we at pi over 2? If we plug in pi over 2 here, what do we get? Cosine of pi, which is -1, which is 0, right? So when I'm looking in direction pi over 2, I shouldn't see a point. You'll notice on this one, when I look in the direction pi over 2, I see a point away from 0. Here I see a point away from 0. This is the only one where when I look in the direction pi over 2, I don't see a point. So that's enough to convince me I can eliminate the other two as options. So indeed, it does turn out it's 2 is the last choice.